A relation is a connection between two or more sets. For us, we will always connect number sets. Now, in graphed, relations look like points, lines, curves, things like that. As you can see with these four graphs here, all four of these things are relations. It's really just a set of connections. Now, within these relations, we can have what are called functions. A function is a relation that passes the vertical line test. And that's going to be a key thing to keep in mind. If you cannot draw a vertical line that intersects the relation twice, then the relation is a function. So all functions are relations, not all relations are functions. Just like all squares are rectangles, not all rectangles are squares. Now, the vertical line test is quite easy to use. All you got to do is draw a vertical line. So in this first relation here, right, I can draw a vertical line where the points are. So this first one, or this point here, I can draw a vertical line here on the y-axis. Draw a vertical line here, 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 and here. Those don't cross twice. However, if I draw a vertical line on these 2 points, that does cross twice. So this is not a function. Okay, for this next one, I can draw a vertical line here, 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 and here. And you can see it never crosses twice. So this is a function. On this relation, I can draw a vertical line right here. It crosses it 3 times. That means it's not a function. I should say real quick on this one, I can draw a vertical line right here, and that only crosses it once, only intersects the relation once. However, if you can draw a vertical line where it intersects it twice or more, then it's not a function. All you have to do is be able to draw one vertical line that crosses twice, just like I did in this first graph. If I can do it once, then that means the whole thing is not a function. Finally, this one here, I can draw vertical lines all day long. Every single one of them will never cross twice, even though this thing continues indefinitely this way and this way. It's still, I will only ever cross it once, every vertical line. So this is a function. Now, functions are written in this notation here, y equals f of x. And f is the name of the function. It's named typically f because f is the first letter of function. And the input is inside the parentheses, so the input is x. The output is what you get when you plug x into f. You get an output of y. So in practice, you won't see the y really. You'll see just an equation here. This equation, you should think of this side of the equation here, x to the 5th plus 3x squared minus 18.5x plus 708. You should think of this thing as f of x. So when you plug in x, you plug in x into these things, you simplify a statement out, and that will be your output f of x. Of course, function names can be anything. This one's just named f because that's the standard name, but you can name whatever. You can name it G, capital H is all capital letters, like capital F, capital G, capital H are common. I like to use subscripts. I think subscripts are a great way to talk about more than just letters for the names. But in all of these things, it's important to note that f of x, g of x, h of x, f1, 2 of x, this is not multiplication. You're saying the name with the input. It's not a multiplication thing. It's just a different type of notation. Now, we like functions specifically, not relations in general. I mean, relations like circles or ellipses, hyperbolas, those kinds of things. Those are relations, and we do use those. But in most of mathematics, you will always be working with functions because we like functions. I mean, functions in the real world don't have to be mathematical. They can be a lot of different things, but they all have the same kind of idea. A function is just a machine. So we have some machine that is the function. You put something into the function. So in this case, it's your input. We will be using the x variable for that because we're going to be using the x-axis on the grid. and that will be our inputs. And then from this thing, the function does something to that input, and it gives you an output. And that will be the y variable, or the vertical axis on the grid. And the nice thing about functions is you plug in one input, you get one and only one output. That's the same thing as saying the vertical line test passing, that if I plugged in an input in this one, my input here was the x value is 1. I got two outputs. I got 0 and 1. Those are the y values of these points. Or sorry, this is a -1 input. So you plug in -1, what do you expect? Well, you can't expect 0 or 1. It can be either one of those two things. And that's not what we like. We like to plug in one thing and know what to expect as the output, and not have to choose between two outputs. Okay, the domain of a function. This is an important concept that we're going to see a lot in these videos. The domain of the function, or any relation, is the set of all inputs that can be plugged into f, of course. So if you plug it into f and you get some kind of error, like for instance division by 0, that is not a valid input. You would exclude that from the domain. Now, since we're going to be graphing on the Cartesian coordinate system, now this is the important bit here, Cartesian coordinate plane. This is a real number system. You cannot have any imaginary numbers in this. So if you plug in an input, you get an imaginary number as an output, that is not allowed. And of course, the domain is going to be the x portion of the graph. And so these are going to be intervals on the real number line. Now, to actually find the domain, there's a couple ways you can do it. You can just find all the x values on the graph. That's probably the easiest way because it's very visual. But you can also check its equation. And when you check the equation, you're asking what values should you not plug in, really? And I'll show you that in a second. Now, for the domains of the functions above, so this is not a function, so we can find the domain of this relation. The domain of this relation are just the x values. So we're talking about this x value, which should be -1, this one here, which should be 0. And then, well, I should say if these are actually by units, because it's not labeled here at all. If this could be, for instance, this could be 10, 20, or probably most likely if it's just 1, 2. And just assuming that it's 1, 2, this would be -1, this would be 0. This point here would be something like 0.2, then 0.4. This one would be like 0.6. This one would be 0.8, and then 2. So those would be all of our domains. So -1, 0.2, 0.4, 0.4, 0.6, 0.8, and 2. Or I should say 1. It's 1.2, 1.4, 1.6, 1.8. That would be the inputs for this relation, but this is not a function, and that's the question asks, what are the what's the domain of the functions? And so this is a function, and you can see that we have a x value for this first point at 0. This one is at 0.5. This one is at 1. This one here is at 1.5, and that one's at 2. So the domain of this function is going to be the set 0, 0.5, 1, 1.5, and 2. This is called a discrete function because I have a countable number of inputs, or I should say a countable number of relations. Because we're looking at only the x values, we have these five things. So this is a discrete function because it's a bunch of points. Now, a continuous function, on the other hand, this is not a function, so we're not going to worry about it. A continuous function, on the other hand, has an infinite amount of inputs that you cannot count. The real number line is uncountably infinite, and so this is a continuous function. And when we look at this thing, it does indeed keep going upwards like this, and keep going upwards like this. And it's not, maybe it's not apparent on this graph, but because this is going at an angle, it's not going straight up. Straight up, it would look differently. You probably see a dashed line, and then this thing gets close to it. That's called an asymptote. We'll talk about those later, but this one doesn't have that. And so we can expect that this thing continues indefinitely to the left and upward. The same thing is true on this side. It continues to the right and upward, which means it will always continue leftward. It'll continue all the way down there and all the way up there. Well, that is the entire real number line. So this function has the entire real number line as its domain, and that looks like the interval -infinity to infinity. And this is what you're going to typically expect for intervals of the real number line. Some interval notation. This one just happens to be everything, but you could also see things like 2 to 7, something like that. These are kind of the normal domains that you should be expecting, not these discrete ones. We're going to be looking at continuous functions, really, or I should say continuous relations and the idea of we're not looking at solitary points. Okay, now, when looking at an equation, it can be helpful to start, like say the domain is the entire real number set, like it was in that function I showed you. Then from that place, we're going to remove issues. So, for instance, in this first function here, we're going to assume first off that the entire real number set is the domain of this thing, and then ask, is there any number in the real number set that when plugged into this function gives us issues? So the real question is can you square, is there a number that you can square, multiply it by this, add it to the same number to the 4th power, multiplied by 5, add those together and then subtract 1. Is there any number that you can plug in there that will cause some kind of mathematical error, like for instance division by 0, the square root of a negative number? That cannot be allowed here because we were working with real numbers on the Cartesian coordinate system. So those are the kind of errors, those are the main ones that you would think of. And in fact, there are no numbers that can do that. You can square any number, you can 4th power any number, you can multiply it by any other number. Like think of it, like we're -1 billion. Yeah, that you can square, that you can take to the 4th power, you can multiply it by things, add them together, even very small numbers. That's no problem. You can square it, 4th power, multiply by everything. All these things are fine. So this domain is the entire real number line. So that's the domain. Now for this next one, again, start with the entire domain of the real number line, and then ask, is there any issues here? Well, hopefully in this one you see, well, if x equals 0, we have 1 divided by 0. So we know that x cannot equal 0. Now, that's this first little fraction. There's actually another fraction, right? We look at this one. Now, what about this entire fraction? Well, this thing can equal 0. 1 over x minus 2 equals 0 when you add 2 and then multiply by x and then divide by 2, you get x equal to 1/2. So when x equals 1/2, we get 1 over 1/2. Let's say 1 over 1/2 here. That's the same thing as 2. 2 minus 2 is 0. We have a division by 0. So x cannot equal 1/2. Well, those are the only issues we have here. The rest of the numbers don't give a division by 0, and you can divide any other number just fine. So these are the only issues. So we're going to do this by doing -infinity up to the lowest value is 0, union with 0 up to 1/2, and union it with 1/2 up to infinity. So we have these breaking points. There's no 0 in this spot, and there's no 1/2 here. All I've done is I've taken the real number line and cut out 0 and 1/2. And that is the domain. Now for this next one, we have a square root. As I said before, we cannot have complex numbers. So the question is when does this thing give us a complex number? Because there's no issue on the inside of the square root, right? You can do 8 minus 13.7 times any real number. That's fine. It's the square root that's the issue. So the question it really is when is this thing negative, right? Because the negatives give you complex numbers. So let's ask 8 minus 13.7x. We're asking when is this thing less than 0, because that will be our problem area. Add 13.7 and then divide by it. That's what we get. We can actually calculate this as an actual decimal number. It looks to be long, so I'm just going to write it as move one place over, 80 over 137, just because I don't want to have fractions and decimals in the same thing. So these are problems. So I could say like x cannot be this. Well, that's the same thing as saying that we only want x to be greater than or equal to 0. That's what we want. So this is the acceptable numbers. And if it's less than, or if x is greater than this, I suppose I should say, because I added x over and then divided by it. If x is greater than this number, then we get complex numbers. And you can test that, right? A number that's greater than, it says x must be less than or equal to this number. A number that's greater than that is 1, right? If you test 1, plug 1 into there, 8 minus 13.7 is a negative number, and that causes an issue. So this is our interval. That's the same thing as the interval negative infinity up to 80 over 137 with a square bracket, of course, because we are allowing the equal sign. So once again, you can just test these numbers into here and make sure they work, right? I tested 1. 1 is just a little bit above this number, and that did not work. You can test this number itself. If you plug it in there, you're going to get 0, and that gives that's just fine. So this is our domain. Now, division by 0, it should be somewhat easier to find because it's really only one number. But the square root has a range of numbers that must be excluded. So I kind of want to look at this a little bit more. Right, if you're asking what's the domain of this function here, well, this is a square root, and we cannot have a negative number underneath there because we're going to have a complex number as a result. And complex numbers are fine, but they're not okay to graph on the Cartesian coordinate system. You can't graph complex numbers on that. So we must exclude those for our purposes. And we know that happens when x, when x is less than 0, which means the domain of f2, the domain is 0 and greater. Okay? Now, for the cube root of f3, the cube root of x, however, is a different story because if, for instance, I could take negative 8, plug negative 8 into there, and the cube root of negative 8 is negative 2. The cube root of 0 is 0, and the cube root of positive 8 is positive 2. So negative numbers actually work just fine. There's no issues there. So this thing actually has the domain of everything. Now this one, f to the fourth, or f4 of the fourth root of x, I can actually rewrite this as x to the 1/4 power, which is the same thing as x to the 1/2 power. And the point of doing this is that there's actually hidden within, in fact, every even root, a square root of some kind. There's always a square root inside these even powers. So, I should say even radicals. So that means that we know everything negative cannot be plugged into this. And in fact, 0, the fourth root of 0 is 0, fourth root of 1 is 1, the fourth root of 16 is 2, and so on and so forth. So all positive numbers are fine. And for the fifth power, this is actually the same thing as the cube. There is no issues there. You can go ahead and try it out in your calculator. Just try a bunch of negatives, 0, positive numbers, and they're all going to work. Now, what about things like this, where we have some expression underneath of there, where a and b are just some real numbers? Well, we know that this cannot be negative. It can't be negative, so we're going to make it positive or equal to 0. We're saying that this is the domain. Then all we have to do is add x. And you're going to see we have x must be less than or equal to a. That's because this negative sign there. Because of that negative sign, that means that positives are actually the issue here, not negatives. Negatives will cancel with that negative, and this whole thing becomes positive. Of course, the a will shift where it starts, but this means that x is everything up to a. So if a is negative, it's going to be, no positive values are fine. If a is some very large positive number, like for instance 1,000, then everything up, all the positives from 0 to 1,000 are going to be fine, but everything above that is going to be an issue. And we already looked at this thing. Everything is fine here underneath the cube root. So this was m of x. N of x has a domain of everything. Okay, pause the video and give these thought processes a try in number 1. All right, so we talked about domain. Domain was all the x values. The range is the set of all outputs, or y values. And these are going to be the ones that are produced from f. So if you plug in an input, you get an output. The output is in the range of the function. Now, like domain, these are also going to be intervals of the real number line, because we're talking about the Cartesian coordinate system. You get only real number allowed to graph on here. So this is really the easiest to see, is all the y values on the graph, like I said. So in this first one, we have, what are the ranges? This is a function, of course, it passes the vertical line test. What are the range? Well, the range looks to be, let's see, that's 1, that's 3. It looks like the set, this is a y value of 0. This is a y value of what it looks to be 0. That's going to be 1/2. That means that must be a quarter, 0.25, or 1/4, whatever you want to do. That's a y value of 1. This is a y value of what it looks to be 2.25. Yeah, because that's going to be 2.5. So half of that is 2.25. And then finally, this y value here is at 4. So that's the range for this discrete function. It's just a bunch of dots. For this one, you can see that the graph extends indefinitely upward because it goes off the page. So that means you just keep the trend going. And you can see the lowest value here is at 0, the y value of 0. It doesn't go below that, so we know it must start at 0. And all of these y values, all of this stuff is included in the domain. Let's do a different color here. Or I should say range. All this stuff is included in the range because I can go over to the function and that gives me a y value at that spot, and keep going back, keep going back, keep going back, all the way up forever. So that means this thing has a range from 0 to infinity. Okay, this is a function. You can take a vertical line anywhere you want. It's a function. And what are all the y values of this function? Well, these look to be the lowest y values, and those correspond back here to -1. This one as well. As you can see, we have a solid line all the way up to this top value. This top value here is at 1. And since it's a solid line all the way between those two things, everything between there is going to be in the range. So all of the y values of this thing is going to be from -1 to 1, and we are including both the endpoints, so they get brackets. Okay, so that's how you can see domain and range from the graph. If the graph is simple enough, actually, we can do more than just find the domain and range. We can also calculate values. So the domain of this function here, it's a solid line. We're assuming that these endpoints are in there. They would have open dots if they weren't, but in this case, they're closed dots, so we're going to assume it hits both the endpoints. And you can see the domain is all the x values. Well, this is the furthest left x value we have, and that corresponds here to -1. And all of this stuff is included, all of this stuff of the x values, these x values all the way go up to here. This is the rightmost x value, and that happens at 7. And all the things in between are evaluated there. So all these have x values between -1 and 7. So the domain is -1 to 7. Now, the range, I'll let you kind of look at this and figure out the range. This is what I get for the range, and see if you get the same thing. Okay, the x-intercept is where the graph intersects with the x-axis. The only point of intersection is right here. And that, of course, happens at an x-intercept of 2, 0. But, of course, you don't really use the coordinate of the x-intercept, or sorry, the ordered pair. You would always say the x-intercept is 2, because the y value has to be 0 at an x-intercept. Since it hits the x-axis there, y is always 0 there. So you would really say x equals 2 for the x-intercept, or just 2. The y-intercept, likewise, is where it crosses the y-axis. That happens right here. And that is at a y-coordinate of -3. So you'd just say -3. You could say it's at 0, -3, but that's kind of pointless because all y-intercepts have an x-coordinate of 0. Okay, to evaluate a function with an input, so we're given an input here. The input is 5, and we're plugging it into the function j. Of course, this is function j of x. I should have said that in the beginning. But we're plugging in 5. Now 5 is an input. That means it's an x value. So to find this evaluation, what's the output of 5? We go to 5. 5 is right here on the x-axis. When you plug it into an input, you go up or down to the function. In this case, we do not go down. There's nothing down here. So we're going to go up to the function. And the output is the same thing as the y value. The y value is 3. So j of 5 is 3. Here we have an input of 1.5. 1.5 is, let's see, right here. We're not going to go up to the function. There's nothing up there. So we're going to go down. And that is right on -1. So you plug in 1.5, you get out -1. Now these next two, we do not know what the input is. We're actually trying to find the input. And we're asking if the output is -2, what must the input be? Well, the output is the y value, not the x value. The output is -2. -2 is right here in the output. In this case, we're not going to go up or down because that was the input. We're going to go left or right to find the input that got us there. In this case, we're not going to go left because there's nothing over here. The function is not evaluated over here. We're going to go right. And this point came from the x value of +1. J of +1 goes to -2. So if we want an output of -2, we have to plug in 1 to get it. I can say j of 1 equals -2. Okay, for the next one, we have an output of 2. 2 is right here on the y-axis. We're not going to go left again because there's nothing over here. We're going to go right. In this case, we have actually 2 inputs give us this output of 2. The first one is 3, and the last one is 6. So both 3 and 6 give us an output of 2. So I could say j of 3 equals 2, and j of 6 equals 2. All right, let's look at another one here. This one, of course, the pattern continues this way. And the way this is drawn, this is actually what's called an asymptote. We're going to look at these more later on. But this function gets closer and closer to the x-axis, but never crosses it. That you can see because if it did cross it, you would see a point of crossing. In this case, it gets closer and closer and closer to it, but never crosses it. So the domain here is quite simple. It continues indefinitely this way. So that means all these x values all the way down to negative infinity are included. It does kind of like it goes straight up, but it doesn't, because you would see a dotted line there. This keeps going up and to the right, which means all of these things are going to be included in the domain as well. All these x values are included here. So the domain is the entire real number line. The range, well, I told you that this thing gets infinitely close to the x-axis, but never crosses it, which means there is no x-intercept. This thing does not cross the x-axis. It gets, however, infinitely close. So we know that the smallest value is going to be 0, because this is at y equals 0, but it never hits that. And you can see, well, it continues up indefinitely upward. So all of these values are going to be in the range all the way on up to positive infinity. So that is our range. Note that it's not a square bracket next to 0. It's a parenthesis. Okay, x-intercept, it never crosses the x-axis, so there can be no x-intercept. There's no intersection, so no x-intercept. The y-intercept, that one's easy to find. That's just right here at 1. Now we just need to start plugging in values and finding what is the evaluation. So f of 0, plug in 0, what do we get? Plug 0 into the function, you get the y-intercept, which is at 1. So f of 0 is 1. If you plug in 1, what do we get? Plug in 1 in here, go up, and that is at 2. So f of 1 is 2. We're going to plug in -1 down here, and that is at, it looks to be, and I know for a fact it is, it's at 1/2. Okay, what is the input when the output is 4? 4 is right here. We do not go left. There's no function over there. We go right. And that happens from an input of 2. So f of 2 equals 4. Okay, give it a try in number 2 and 3. A piecewise function has different equations for different parts of its domain, and that's the important bit here. Is typically when we talk about parts of the function, we're always looking at the domain, not the range. The domain is kind of what your inputs are, those you choose. So those are what are called the independent values. The range depend upon the domain, so that's why the range values are dependent values. So everything is based on parts of the domain. Piecewise function has different graphs for each part of the domain. So here we have a piecewise function. This is how it's gonna be written as you see it. This curly brace and then the different equations. So the first one has -2 for when x is x is less than -4. So anything less than -4, we're gonna use this function or this equation. If it's between -4 and -1 equal to -4, we're gonna use this function. And finally, this one for when x's are greater than or equal to -1. And we're asking what's the domain, the range, and then what are all these values. So to do this, I've got Desmos here, an embedded Desmos thing, and I've actually graphed each part. So this is how the languages works in Desmos. This is the equation that you're using, and then this is the restriction or the domain portion. So we're using -2 when x is less than -4, -2 when x is less than -4. And then the same thing is true for the other two. And I just graph this in 3 pieces. That's why it's called a piecewise function, because you graph it in pieces. And this is the actual function we get. And this is a function, of course, that passes the vertical line test. And what we can do here is we can evaluate the question. So the first one said, what's the domain range? Well, you can see the domain of this thing is going to be everything. It's going to be all these values on down to -infinity. These values here from this looks to be what, 4? Yeah, from -4 up to -1 are included, and so is all these values on up. Like it looks like it doesn't go all the way over here, but it does. You have to zoom out far enough, and you'll find that this thing covers all these values. So the biggest question between piecewise functions tends to be the intersections. And if you click on a function, Desmos will actually tell you what the evaluation is. If you go all the way over here, it gives you an open dot saying it's undefined and -4. That's because this portion, which was -2, is not defined for when x equals 4. However, this second portion is defined there. So -4 can be plugged into this piecewise function. And that you can see here if we're going all the way over, -4 equals 3. Now, of course, the blue, the middle piecewise portion, is not evaluated for -1. If I go all the way over the other side, you can see I get an open dot there that says undefined. But the last portion, the green one, is defined there. It's defined as -1, 0. So -1 is also fine. That means that the domain for this guy is everything. There are no issues in its domain. If there was, of course, a skipped value somewhere in this domain, then that would be, you'd have to skip that value in the actual domain thing. So if, for instance, we had -2 for when, I should say, x less than -4, and this one said -4 less than x less than -1, then and then of course we still had the last one. You would say it's from -infinity up to -4, -4 to infinity. You just cut out the -4 from that, the entire real number line. Okay, now the range is a little bit more interesting because the range here has a jump, right? These y values are all at -2. And then there's a jump here between -2 and this portion. Of course, this portion, lowest value here is at 0. And then it does, in fact, all of these values on up. You can find every single y value from 0 on up. So everything from 0 upward is in the range. And then -2 is also in the range because these values are at -2. There's this huge jump here, this gap, and this is only a single number, which is not an interval. So how would we write that? Well, the lowest value is -2, and it's just a number, so we're going to use a set. And this is going to be unioned with the interval from 0, including 0, up to infinity. And this is just a fancy way of writing a set itself, the interval notation. So you union two sets. This is a set, this is a set, so you union them together. That's how you can write this range. Okay, p of -10, to find this value, we're going to plug it into this function here. P of -10 says that we are in this portion of the domain. -10 is less than -4, so we're going to use this one. We would not use this one because -10 does not fall in this range, and -10 does not fall in that range either. So P of -10, you plug -10 into here, well, you only get -2 as an output. You get -2. What happens if you plug in -2? P of -2, -2 falls in this range here. So we're going to plug -2 into this guy. Negative of -2 is +2. 2 minus 1 is 1. P of 0. 0 falls in this range again. -0 is 0, minus 1 is -1. And finally, P of 10. 10 falls in this range here. 10 squared is 100, minus 1 is 99. Now, you don't have to do this process. We have the graph here, and we can just find the value. So -10 is our input. -10 is right here. And you can see our output is at -2. So we know that P of -10 is -2. The next input was -2. -2 is right here. And looking at that, there's our output. Our output is a +1. Okay, P of 0. 0 is here. So we go down to our output. That is the y-intercept of -1. And finally, P of 10. 10 is right here on the x-axis. So we're going to zoom out, go way, way far up here. And there it is. 10 goes to 99. All right. Now this is what I was doing. I was plugging the input into the function using the function notation. And this is the value of function notation, is you get your inputs and your outputs all in one go. So our input is -3. So if we're going to first write this in function notation, the way it works is you just solve for y. I'm going to add 3y and then subtract 5x. That's going to give me 3y equals 3 minus 5x. Then all we have to do is divide by 3. And the way function notation works is you replace y with f of x. So f of x equals 3 minus 5x over 3. And the proper way of writing this is you would say f of -3 equals, and then plug this value in wherever x occurs. If it occurs more than once, plug it into each occurrence. In this case, it only occurs once, so we're going to plug it in, and we're going to use parentheses when we plug it in. So we have an input here, and our input is here, just like our input and our input. Okay, now all we have to do is calculate this. 5 times -3 is -15. Negative of -15 is +15. 3 plus 15 is 18, divided by 3 is 6. So, f of -3 equals 6. Our input's -3, our output is 6. Okay, next one says plug in 3/5. Okay. 5 and the 5 cancel, and we get 3 on top. 3 minus 3 is 0. And of course, that just equals 0. So f of 3/5 equals 0. And that means that this is our x-intercept, because y is 0. That means this is where on the x-axis. And if the function crosses the x-axis, that is an x-intercept. So the x-intercept at 3/5. Okay, here we're plugging in an expression. That means typically you're going to get an expression out. So plug in x plus 7. Our input is right here. So we're going to go 3 minus 5 times the input, which is x plus 7. And the best we can do here is expand this thing. This is just an expression that we have to combine like terms for. It's going to be minus 35. 3 and -35 gives us -38. Or no, -32. So f of x plus 7 is a different function. We're going to be actually studying this a little bit more. This is actually somewhat of a what's called a transformation, but we'll be looking at this a little bit more. So it just gives us another function. That's all we're saying here. Finally, if you plug in -x, 3 minus 5 times the input over 3, we get 3 plus 5x over 3, and that's the best we can do. So f of -x equals that new function. All right, give it a try in number 4.